Some new theory about radical equations. A radical equation is an equation where x appears underneath the radical sign, as the one given here in example 1. Now, in order to get to the x underneath the radical sign, we need to square, we need to get rid of the root. So we will always square. But if you squared now, on the left-hand side, you would have to use the perfect square formula, right? It's a binomial, a root minus 1 all squared. This is something you might not voluntarily want to expand. So let's first get the root on one side before we square. We isolate the root by adding 1 on both sides of the equation. We end up here, okay? And now if we square, we actually do get rid of the root. Squaring here yields x plus 7 equals x plus 1 all squared. Now naturally you can go on from here. You have now turned your radical equation into something you're used to solving. We end up here. We see that it's going to be a quadratic equation, so we take everything to the right. One side equals 0. We get x squared plus x minus 6 is 0. And if we then factor, we find that x minus 2 times x plus 3 equals 0. From this we can find the two solutions. The equation has x1 equals 2 and x2 equals negative 3. Okay? So far so good. Now let's look at the second expression. Sorry, I actually wanted to highlight this also, because that's the key point of the first item here. Isolate the root before you square. Now the key point of the second item is whenever you solve a radical equation, check your solutions. Check by plugging them into the original equation. Now why should you do that? You know that you can always do that, and you have always been doing that in the past, but why is it necessary? It's necessary because squaring is not an equivalence transformation. When you have an equation and your usual way of solving them is, say, to add 3 on both sides, might be beneficial. If you add 3 on both sides, the new equation you get still has the same set of solutions as the original equation. However, if you square, this is not always true. Here in the example, we start out with a very simple equation. X equals negative 3. It's obvious what x is, negative 3, right? If we square this, what we get is the equation x squared equals 9. Now you do of course know that x squared equals 9 has two solutions, namely plus 3 and negative 3. Apparently we got our equation no longer has the same set of solutions, but we introduced a new and additional wrong solution into the equation. Okay, this step here, well, it's not entirely wrong because the new equation still has our original solution as a solution, but it also has an additional erroneous solution. Well, the consequence is we need to check. And if we do that for our example 1, for x equals 2, if we plug in 2 into the original equation, we need to check whether the root of 2 plus 7 minus 1, whether this really is equal to x, namely 2. Well, what we get on the left-hand side is the root of 9, so 3 minus 1 equals 2, yes. Great. That's fine, and we can underline our result here. For x equals negative 3, if we plug this in, we get the root of negative 3 plus 7 minus 1, and the question is whether this really is equal to negative 3. And as you can see, negative 3 plus 7 is 4, the root of 4 is 2, so we end up with 2 minus 1 equals negative 3. Well, and that's wrong. Okay, so this not really is a solution. That's very important. You need to check whenever you square when solving an equation, and because you always square when you solve a radical equation, you must always check your answers when you solve a radical equation. Okay, now let's look at the third item here. This is sort of an extension to the second item. It's not really new, but well, you need to be careful when you're dealing with roots. This more straightforward equation, I dare say, here root of x minus 4 equals root of 2 minus 2x is solved directly by squaring. We have both roots isolated on either side of the equation, and when we square, both will vanish at the same time. So squaring here leads to x minus 4 equals 2 minus 2x. Rearranging, adding 2x and adding 4, we find that 3x equals 6 or x equals 2. Alright, now if we know we have to check. If we do check, what we find is the root of 2 minus 4 equals the root of 2 minus, well, 4. And I mean, this sort of looks promising, but on both sides of the equation we have the fancy expression, the root of negative 2. And that's not something we're comfortable with. This tells us that this does not make any sense at all, even if it almost looks as if the two sides of the equation were equal. If we are working with illegal expressions, we cannot be pleased with our solution. So here x equals 2 has proved to be not a solution, not a reasonable solution, so there is no solution. Well, the plural is not really necessary here, no solution. Alright? That's what you need to know about radical equations.